Welcome to the first lectures. So this is a turn lecture course by Charlotte Chan of the University of Michigan. And she's going to talk about Deligne-Lusztig theory, examples and applications in her course, and today about Deligne-Lusztig varieties.
Hi, everyone. Thank you very much. It's an honor and a pleasure to be here. So let me say a little bit about my interests. So I'm interested in representation theory, and especially in its interactions with algebraic geometry and number theory. And so I hope in the next week, both in my course and also in Anna's course, you'll get some sense, maybe a glimpse, to take a word from Anna's title, into some of the very deep ways in which these subjects inform each other. And there will be some appearance of other subjects as well. We'll have a little bit of topology at some point, maybe a little bit of analysis. And so we get a sense of how close everything is in some sense. So let me say, representation theory, which just for right now, I'll abbreviate as RT, can be viewed as the modern study of symmetries. And it has many, many applications beyond the scope of pure mathematics as well. So in chemistry, for instance, I have a good friend who's a professor in chemistry, and there they make molecules in the lab by, I guess, putting some stuff together and something comes out. And they kind of know like what the atoms were that went into the molecule, but it's important for them to know the molecular structure. And to do this, they use character tables from representation theory. So this is just one example of the many things, the reach that this subject has. So let me start by defining what a representation is. So I think it's pretty safe for at least the first few talks of mine to assume that G is a finite group. And later on, actually, like in 5 minutes, this G will be a specific finite group as well. But just for this definition, yeah. So a representation of G is a vector space over C. I'll actually always have finite dimensional vector spaces. Endowed with a linear action of G. And so what linear means is that this action has to respect the vector space structure of this, let me call this vector space V. It has to respect the fact that you can take a vector in here and scale it by anything and see that you can add two vectors and this kind of thing. So that's what linear action means. Let me say as a comment that, first let me say, we say V is irreducible if the only G stable subspaces of V are the zero vector space and the entirety of V. Okay. So this is the kind of object that we will talk about a lot this week. And if this is a definition that's familiar to you, fantastic. You'll get to learn about the representation theory of a particular G this week. If this is not familiar to you, you can use the representation theory of the particular G that we will study to learn about representation theory. So here's a side remark and maybe slash exercise, and there will be a lot of this kind of thing, a remark slash exercise, and this is optional homework. I mean, everything is optional, but is that this definition, representation of G is equivalent to the data of a group homomorphism from G, I'll write it here, to GLV, which is, say, if this is n-dimensional, you choose a basis of V, and this is simply GLNC. This is an exercise that you can think about. So let me give you some examples. So a representation that every single group has, and I think this is the only representation that every single group has, is the trivial representation. And so this says trivial. Sometimes we just call it trip. So this is, you take a one-dimensional vector space, that's just C. And now to make this a representation, I need to tell you how G acts on this. So let me tell you how G acts on it. So if I have some element of D and some element of C, which I'll call V, I can declare an action of G on V to be equal to V, as it does nothing. It doesn't depend on G at all. So this is called the trivial representation because the action is trivial. There's nothing happening here. And this is definitely irreducible because it's a one-dimensional vector space, and there are no non-trivial subspaces of a one-dimensional space. Okay, so here's the first. This is the first example. Let me do another example that has kind of a flavor of some of the things that we'll see, even though it's for a rather different group. Let's take G to be Sn, the symmetric group on n things. So this is all ways to permute n things. Or another way to say is all bijections between like the numbers 1 through n to itself. Okay, so this is definitely a finite group. And what we can, so this thing acts on, let's say like x1, let's say x1 through xn, like these are just some, give me 1 sec. Okay, yeah, let's write it in this way. So this is just a finite list of objects. And what this means is that G therefore also acts on the space of functions of these things. So the space of functions from x1 to xn to C. And how does this act? Well, it acts on this thing. And so given any such function, let's call this f, I can, and any element in here, let's call it G. So G is a permutation of these n things. I can have G f on this function on these n things, send whatever value of xi here to f of whatever the value is of G of this thing. So G acting on xi. So the reason I made some noises earlier was I realized that maybe actually it's clearer to write like Sn acts on 1 through n. This is a function that takes the numbers 1 to n to some numbers. And then this is then defined as G acts on f of I by sending it to G of, or f of G acting on that number I. It's the same thing, it's just that, yeah, it's in the lower side. Okay. Okay. So now we have some adjective. I give you a definition. Every time I write something on the board, you should check it with whatever adjectives I put. So we should ask now: is this representation irreducible? And the answer is no. So not irreducible. And the reason is okay. Well, so here's an exercise. Is that one should check that actually there's a copy of the trivial representation inside here. So trivial is inside this representation, V. So this space here is a space called V. And so let me say how to see this. So consider the subspace of all functions with what f of xi is going to be equal to f of xj for all I and j. So f of x, wherever it sends x1 is the same as wherever it sends x2 is same as so you should think about why that's the same as the trivial representation. Okay, but the other thing you can do now, okay, so we have one representation in here, and something a little bit miraculous happens. So it turns out that in the complement of this, so let's say this is a one-dimensional thing, and this is an n-dimensional thing, right? So there's n-1 dimensions that we haven't accounted for, and so here's an exercise is to find a G stable n-1 dimensional subspace of V. And then part 2 is prove it's irreducible. So in this case, what we see is that we constructed some space of functions. It wasn't irreducible. It had the trivial representation inside it, and it has this other representation inside it. And those are the only two. Those are irreducible components of this representation. Any questions to hear?
Question.
Yeah.
I'm wondering for this, is that going to be a right action? Does it matter what's?
Okay, so either right action or a left action, and you can send it to the other one by putting an inverse here.
Okay, does that matter for a producer?
No, it won't matter. Yeah, the question. Oh, yeah. Yeah, handedness is very difficult. Yeah, a choice between two things. It's quite a exercise to move these boards, actually. Wednesday evening, some of us will go to the climbing gym, so side remark about exercise. Okay, so now, unless otherwise stated, I'm going to take G to be SL2 FP. FP is a finite field of P, consisting of P elements, so P is a prime here. P is a prime, and it's not going to be 2 for us. I agree it's prime though. And this just consists of all matrices that look like this, where A, B, C, D are in FP, and AD minus BC is equal to 1. So all determinant 1 matrices with coefficients in FP. This thing is a finite group. And if you two now calculate the order of this group, it will be relevant later. So do that. I will ask I will ask someone to tell me what the order of this group is. And so let me tell you something about the representations of this. And it's going to look a little bit like this model where you have functions on some space. So let me do put an inverse here. Okay, so consider, so whenever we do representation theory, one important thing to kind of start with is some understanding of what some natural subgroups of these things are. So inside SL2 FP, there's something called B. B stands for the human Borel, and it means all upper triangular things inside G. And inside B, there's a T, and T stands for the word torus. And this is all diagonals inside G. Okay, so you should also calculate the orders of these subgroups. This guy over here, now notice we have determinant 1, right? So I'm allowed to put anything here, but the moment I specify something here, then it's going to specify what I have here. So it's going to A inverse. And my A is allowed to live in FP. But it can't be 0, of course, so it's going to be FP star. So this is the same as FP star. So we know order of this one now is P minus 1. Okay, so here's something that happens. So now B contains T as a subgroup. Actually, we have a map in the other direction as well. So there's a map this way. And the map this way goes by forgetting whatever's in the top right corner. So it's a natural surjection. And this is an important map. I'll call it PR for projection. Okay, so the definition, let theta be a map, a group homomorphism from T to C star. And per that remark, this is the same as a one-dimensional representation of T. Okay. So this is a map from T to C star. Since I have this map from B to T, it means that I can just take the pullback of this thing along this map and I obtain a map from B to T. So from this, I can obtain a character theta, a representation theta, which comes from first projecting to T, then doing theta. Yeah, I'll call that theta tilde. But it's basically nearly the same information. There's not anything, yeah, you should think of this theta tilde as being essentially the same as theta. The parabolic induction of theta is the following recipe. I will call it RTG theta. And that's telling you where the character began life and what kind of representation you're going to obtain. It's defined as the induction from B to G of theta tilde. And the induction is defined to be all functions from G to C satisfying a nice property. And the nice property is that no matter what function you take, if you include a B on the inside, on the right, then this is going to be equal to nearly f of G, but up to some shift by this character here. So for all G inside G and all B inside B. So this is what we'd call some kind of equivariance condition. So it has some nice behavior with respect to some action. And over here, so in what way is this a representation? We have an action of G by the same recipe over here, which I corrected to be, I think this gives a left action. It goes like this. So this will act on this by f of G inverse x. So an important thing to note here is that the B is on the other side, it's on the right side. So it's kind of not really interacting with this G. It won't mess up the G action. Okay. Okay, so let me tell you a fact about these representations. There's an extended exercise on the problem set walking you through how to verify certain parts of this. I think maybe actually how to verify all parts of what I'm about to tell you. So here's the fact. Let me check. Okay, here's the fact is that trivial representation should always be on your mind because that's the starting point of a lot of stuff. And so the first kind of character like this should be trivial representation. And what does that do? That just sends every element of T to 1. Because that's like 1 times. 1 times doesn't change anything. Okay, so what this turns out to also contain the trivial representation, and the proof of that kind of has a similar flavor to this exercise over here. So everything is kind of, even though it's a different group. So trivial representation is inside this guy here, okay, so. And then it turns out that there's one more piece, and those are the 2 irreducible components. This extra piece is, I'm not going to say, okay, I'll say what it is. Okay, it's often called Steinberg, which is a person. So let's calculate the dimension of these things. So did anyone calculate what's the order of SL2 FP? Yeah.
P plus 1, P minus 1.
P plus one, P minus one, great. Okay, what about order B? Yeah,
P minus one?
P minus one. Great. What about order T? Oh, I told you already, okay. Okay. So we should be able to try to figure out what the dimension of this thing is. And let's look at this definition here. So this definition tells us that on the right, that it's kind of given by, I mean, okay, what do I mean here? This thing here is telling you that you don't have that much control up to this right multiplication by elements in B, right? So you can't write down any old function, like a random function will not satisfy this. So what kinds of function will satisfy this? Well, one thing you could think is well, if I am fixed up to, or I'm constrained by this right action of B, then maybe I can tell you where to put any particular coset representative of G mod B, and then this will specify the thing. And so that turns out to be true. And so the exercise here is to verify that the dimension of RTG theta is equal to the order of the set G mod B, and the order of set G mod B is the amount of stuff inside G divided by amount of stuff inside B. And we see here, this number is P plus one. We know trivial representation is a one-dimensional thing. This thing is P-dimensional. Actually, it turns out this is the only P-dimensional representation. Okay, so that's one thing. Okay, here's another thing that can happen. So this thing is FP star, right? FP star has order P minus one, and we've assumed that P is odd. So P minus one is even. So there's exactly one character that has values in plus minus one. And so that character has the following, I'll call it sign. There's a sign character from T to plus minus one, which is of course living inside C star. And so then one could ask what happens here? RTG of sign. What happens here? This one is a little bit tricky, but there is an exercise walking you through why the following statement is true. So it turns out this also decomposes into two irreducible representations, but trivial is not inside here. That's an exercise, you can check that. It turns out this one breaks up into two different pieces that have the same dimension. So they're each gonna have P plus one divided by two. So this is gonna be a P plus one divided by two dimensional thing, plus another P plus one divided by two dimensional thing. And they're not the same. So these things are not the same. So this one is a little bit tricky, but the rest are actually easier. So if theta is not sine or trivial, and this is the same condition as saying that theta squared is not trivial, then RTG theta is irreducible. Okay. So this is our list. So here, this one, we said the dimension already. This is P plus one dimensional. And there's an additional fact about this. These guys also, RTG theta is the same as RTG theta inverse. Okay. So you get some overcounting here. Okay. So a fundamental question in representation theory is, okay, so first I hopefully convince you that we want to look at irreducibles. Are these all the irreducibles? That's a natural question. Are these all the irreducibles of G? Okay, so let me tell you a theorem of Frobenius from probably more than a century ago. So I learned while preparing for this Wikipedia that Frobenius was born in 1849 in a place called Charlottenburg. Okay, so this is what Frobenius said. So Frobenius says that if pi1, this is a 1, pi2, pi d are the irreducibles, are all the irreps of some G, and this applies not only to our particular G, all finite groups. Then, if you take the dimension of pi1 and you square it, you add the dimension of pi2 and you square it, and you add the dimension of pi d and you square it, this number is equal to G. This is amazing. And there's lots of, actually, if you want to get into this, there's lots of really cool arithmetic things about the behavior of these dimensions relative to this. For example, the dimension of any of these has to divide the order of the group G. Definitely not obvious. Okay, so now I'm going to erase something. Okay, good. What do I erase? Maybe I just erase middle stuff. Okay. Actually, while I'm my serious business. So I enjoy rock climbing very much. I'm not that good at it, but that's kind of not the point for me. But I have gained mathematically through rock climbing. I've met many people in mathematics who rock climb, and it's a lot of fun to talk about math and climb at the same time. In fact, I even met a collaborator this way. So I'll actually tell you a little bit about some work that collaborator and I did on Thursday, I think. So let's apply the theorem to our setting. So I have a list of representations over here. The question is whether or not it's complete. And what this theorem says that it's complete if I sum up all the squares of the dimensions of the ones I know about, and it reaches the entire size of G, which I have erased, but everyone should remember is P times P plus 1 times P minus 1. Okay, so let's count them. So there's one guy over here of dimension 1 and one guy here of dimension P, and then there's 2 of P plus 1 over 2. And then just before we start writing things down, let's write down how many were over here. So one thing that is may not be clear is that the number of these characters, theta of T, is equal to actually the size of T, and that's equal to P minus 1. And so over here, there are P minus 1, minus 1, minus 1. So P minus 3 choices for this. But I also told you that there's this kind of behavior where you overcount by 2. And so the number of these is going to be equal to P minus 3 divided by 2. So now let's take this sum. Okay, so let's apply to our setting. I get 1 squared plus P squared plus P minus 1 divided by, P plus 1 divided by 2 squared, and there are 2 of them, right? So 2 of these. Plus the P plus 1 squared over there. And the number of those, as we just calculated, is P minus 3 divided by 2. Okay, so we were trying to get to order of G, just P times P plus 1 times P minus 5, right? And roughly, this is like P cubed, right? And what do we see here? So we can at least make a estimate. You can add this out if you want. The P squared is like not the same as P cubed. So let's ignore all the P squared stuff. And the only thing contributing to P cubed will be this guy here, right? P. But I have it divided by 2 here. So this thing is roughly p cubed over 2. So already we see that actually we haven't found all of them. Roughly we've found only half. Okay. And so this kind of thing is the way the irreducibles look. Doing this thing that I told you about, parabolic induction, we only get half of them. And in general, it's kind of like a worse situation. For other kinds of G, you kind of get a smaller and smaller proportion through this kind of induction from T to G. But for SL2, we get half of them. And so let me tell you about how to get the rest. The Drinfeld curve is the following thing. It's all points in FP bar, 2-dimensional vector space over FP bar. So X is an FP bar and Y is an FP bar. This is an infinite dimensional thing. This is the algebraic closure of FP, such that the following equation, xy to the p minus x to the py is equal to 1. So Drinfeld is a person. Drinfeld was studying something kind of some other thing and realized this statement could be pulled out of his work. He was like 15 at the time. Maybe like 19, but you know. Okay, so why does this thing matter for us? So the kind of moral, I think, of representation theory is that first, groups are really important because they capture symmetry. But in many situations in real life, whether that means real life for a pure mathematician or real life for a physicist or an engineer or a chemist, symmetry arises in some natural context, and that natural context is very often a vector space. And for pure mathematician, another place that groups arise is in symmetries of something like this. This is not a vector space, but it's a curve. It's a beautiful object. And so here's the lemma: is that if you take any G inside our SL2 FP, and any, I'll call it zeta, inside the kernel from FP squared star to FP star. So this map goes like this. You take something in here and you map it to x times x to the p, which is the same as x to the p plus 1. This thing is surjective, and this thing has p squared minus 1 elements. This has p minus 1 elements. And so the kernel is going to have size equal to this number divided by this number. So it has size p plus 1. So this thing I'll call mu p plus 1 for p plus 1 roots of unity, but I'll also call it t prime. Again, t stands for torus, and it's prime because it's not the same as the previous one we wrote down. So this is, yeah, okay, like this. Okay, so for any pair, G and zeta, actually there's a way to act on this x. So if I take some x inside here, so, x is maybe bad, x, y, how do you act? So G comma zeta will act on x, y by matrix multiplication on the left and just scaling by this thing. So I'll write G x, y for matrix multiplication, and then scaling, I just put inside. Okay, so x, y, like this, zeta, zeta. So the lemma is that this is an action. I have no clue left or right, so you'll tell me later. Okay. Yeah, all right. So the proof of this is an exercise. And so the question then is, how do we go from this curve, which isn't a vector space, to something like a vector space? And this uses some general machinery. So machine called cohomology, which I will denote by like this. And our i's actually for us, we will only deal with I equal to 0, 1, and 2. But in fact, you have higher ones as well. It just happens that for this guy, you're only going to get stuff in 1, 2, and in 0, it's going to be nothing. And past this, there's also going to be nothing. And what this does is it associates to objects like X, not only X, but things like X, a complex vector space for each I. And as I said, most of the time this complex vector space is 0, but so it has really nice behavior. And this assignment from things like X to vector spaces is a really natural thing. And one of the things that's built into the naturality is that because my X came with some group actions, the resulting thing after I do this machine, after I put it through this machine, will also have group actions. So, I'll write functoriality of HI results in the thing that we really care about, which is that HI of X is a representation of what? Of G times T prime. So all the actions that I had before, G of G and T prime, are still there. So telling you what how to define HI and what all the theory that comes with that is outside the scope of our course. But what I hope to tell you about is how to work with this object. So you don't need to know what the definition is. I'll tell you what the properties are. So the definition is, I'm gonna, so given character theta, a one-dimensional representation of T prime, what I'm going to do is define an analogous thing to what I did over there. So over here we had RTG of something. Here I have RT prime G of this theta. And this is going to be defined to be H0 of theta. Maybe I'll put this in brackets. Minus H1 of theta plus H2 of theta. And what this of theta means is that I'm going to look inside each of these. I'm going to say, oh, there's some part where T prime acts by theta. That's what this HI means, and theta means. Okay, so here HI theta is defined to be the subspace of HI, which remember is a representation of G times T prime, where T prime acts. Okay. And so even though the construction looks very different to what we had before with principles of series, or parabolic induction, the notation suggests that we should think of it in a similar way. I have something that's starting on some abelian thing. This is a T prime now instead of a T, and it's building for me some representation of my SL2FP.
Can I ask a question?
Yes, please.
How should we think of minus at this point?
Yeah, that's a good question. So we know from linear algebra that maybe minus a vector space is not really such a good thing to think about. However, in representation theory, because we also have these this action control that's I guess distinguishing certain subspaces. In fact, there's a way to just think of this, like we should just think of this as a formal linear combination, like Z linear combination of vector spaces. And so when I write this, you should think this is some vector space, it has a group action, it's a representation. This minus of a thing, this thing that I've minus is a vector space, it has a group action, it's a representation, and same with this one. So I write it in this way but actually we'll see that this one, there's nothing there. So in fact, there's only stuff in H1 and in H2, and they're kind of separated out in a way that makes this psychologically manageable. So let me let's write down the analogous thing to over here, and hopefully I can convince you that the picture should be thought of as in complete parallel. Okay, so I erase this now. This is way worse than this. Okay. So here's a fact. And this fact, I won't label as an exercise. This is harder than the previous fact to do. But we'll see how to get at least to some parts of this fact, I believe. So as usual, we start with trivial representation because this mu p plus 1 t prime definitely has a trivial representation. You set every element to 1 in the map from t prime to 1. So let's do that. So say theta is trivial. What happens to this one? So it turns out what happens to this one is that this guy will have the trivial representation, and it will be only the trivial representation. So our H2 over here will be trivial. And this H1 will contain a p-dimensional representation, and it turns out that's the same thing as this Steinberg thing that I wrote up there. So in this situation, it turns out that H1 of triv is equal to Steinberg, and H2 of triv is equal to the trivial representation. Okay, so in some sense, you should see this and you should be a little bit disheartened because we didn't gain anything from doing this complicated stuff. But the next thing I'll write down gains us something. So if I take RT prime G of the sign, now it's a different sign character because that one was on this FP star, and which was p minus 1 size group, and this one's on a p plus 1 size group. So this is a different sign, but it's still the fact that p plus 1 is an even number. There's a unique group homomorphism from this t prime to c star that maps into plus minus 1. That's not the trivial one. So in this case, it turns out everything is inside H1. So actually, this is the same as just minus H1 of sign. So this minus is just a formal minus sign, as I said before. And what is this thing? So this thing turns out to be minus, and then it also breaks up into two distinct irreducible representations, and they are the same dimension. Okay, so what dimension is that? So a fact here is that the dimension of of RTG prime G theta is equal to p plus 1. Yeah.
How should we be thinking about T prime and related? Right now they seem kind of unrelated.
They are unrelated. I think you should think of them as two abelian subgroups of G. Yeah, great question. Yeah, so a more sophisticated answer to this is that T and T prime are both what are called maximal tori of SL2. Now, maximal tori, I mean, a torus by definition is something that looks like GM, which is like a product of like FP stars or FP squared stars. And this one's definitely not an FP star. It's not a product of FP stars. But what happens is that as a group scheme, this thing becomes a split torus if you go to a degree 2 extension. And so that's the sense in which it's a torus. So torus always means GMs, and this one is what's called a non-split torus. But I think, The important thing is that they're different and both abelian. So this one is splits into this, no. P minus one, so equidimensional things, there's a P minus 1 over 2 thing, plus a P minus 1 over 2 dimensional thing. And so just from comparing dimensions, we already know these ones are new, right? They didn't appear in previous lists. And then you can guess what happens next. The next thing, the third bullet point is the same thing as this bullet point. And I could just write exactly. So theta not equal to sine or trivial, which is the same thing as saying that theta squared is not trivial. This should be infinitely F. Yeah. Then RT prime G theta is irreducible. And in fact, this thing is also, it's only in H1. And also, if you look at RT prime G theta, this is the same as RT prime G theta inverse. So now we can calculate how many of them there are. There are P plus 1 such thetas. One of them is given by trivial. One of them is given by sine. And so over here, the number left is P minus 1. And I have this symmetry with theta and theta inverse. And so the number of these irreducibles I'm getting is P minus 1 over 2. Okay. I like this one. So let's modify now. We want to apply theorem to our setting. Let's erase this. But now we add. So we have the 1 and the P. That doesn't change. We don't get to add anything. But we have two P minus 1 over 2 dimensional ones. Okay. And then we have P minus 1 divided by 2 P minus 1 dimensional ones. So here's the exercise. Don't make me do this up here, please. Is that this is equal to G, which, as we saw before, is P times P plus 1 times P minus 1. This is amazing. Oh. Took a bunch of numbers that didn't seem to have any relation to each other. Take sums of squares. It's equal to this. It's amazing. Oh. Okay. So let me. Okay, so while you guys finish copying, I'm going to stand here for a minute and decide what is least important. And so I can erase it. Okay, so.
Wait, I just have a quick question.
Yes, please.
Can you find the P plus 1 first root of unity, or is it that minus the minus 1?
It's the whole thing. New P plus 1. Yeah, it's that group. Yeah. Yeah, very good. So I think the question was that there are some things that are in mu P plus 1 that are also in FP star. And exactly those two things are the identity and minus 1. And so the question was, are we taking this to be the stuff that's not already covered in FP star or everything? So this is the all mu P plus 1 roots of unity. Yeah. Okay. So here's the recap. Is that half the EREPs came from theta, one-dimensional representations of T, and half the EREPs came from theta, one-dimensional representations of T prime. Okay. And even though I presented them in really different ways, it turns out actually these are two examples of the same story. And so let me show you how to do that. So I guess maybe I should write it here, secret. These are two examples of the same story. Which is and the content of this is that this thing can be unified. This is really part of one picture. So in the P set, there will be a problem that tells you the following thing, is that SL2FP, but in fact, this is true for anything. So I'm just going to put a K here. But I think on the problem set it's written for FP, it will not affect the proof. This thing, yeah, I'm gonna write it for FP and just know that you can change all the coefficients to something else. The SL2FP as a group has the following set theoretic decomposition. It consists of stuff that's upper triangular. Okay, it's a totally reasonable thing. And then it consists of stuff that is kind of almost upper triangular. So this is saying that everything inside our G is either inside here or inside here. And this is called Bruhat decomposition. Okay, and so here's the lemma, which is an exercise. This is also in the problem set. Is that if you take all G that are in SL2 FP bar now, FP bar, where G inverse sigma of G is inside U I didn't introduce yet. Okay, U is also really important. U stands for the word unipotent. And so U is a set of all things that look like this. So in fact, this is also an abelian subgroup of SL2. And so one could ask, if our whole game is getting from abelian like representations of abelian subgroups of SL2 to representations of SL2, what happens when you take this one? And this is really important as well. So this kind of thing maybe is called Gelfand-Graev or generic representations. Whittaker model. Those are the kinds of things that you might have heard of before that relate to this picture. Okay, but it's not our main focus, but it's very closely related. So that's what U is. If you take this quotient by U of FP, so this one will mean the one inside our G, which is FP part. It turns out that this thing is simply the same thing as G mod U. That's the first thing. And the second thing is that if I take all G inside SL2 FP bar, sorry, where G inverse, I did not tell you what sigma is. Ask me what sigma is. Okay, this is sigma. Sigma is so important that so sigma is from SL2 FP bar to SL2 FP bar, where A, B, C, D goes to A to the P, B to the P, C to the P, D to the, oh, I wrote Q. Okay. It doesn't matter if you change P to Q being a power of P, and yeah, so sometimes, okay. So this is sigma. So you should check, this is a group homomorphism. Yeah, so this is all things in here where U of FP bar, and now this one will come in, 0, 1, minus 1, 0, U of FP bar, quotient by U of FP bar. Okay, so the only thing that happened between this line and this line is that this U is like this B. This one is like this one. That's the parallelism. This thing is equal to our Drinfeld curve X. Okay, so this one is just a finite set of points, right? This is something, this is a finite group divided by a finite group. This is a curve, as I mentioned. But in fact, both of them fit into the same story in this sense. It comes from taking this kind of Bruhat decomposition. And so this is something that you can check explicitly. I encourage you to do so, is you will multiply 2 by 2 matrices many, many times and solve some coordinate wise, but I think it's a good exercise to do. Okay, but moreover, what did we have before? So before we had, okay, remember this, machine cohomology, this is important. I will tell you what it means for G mod U. For G mod U, it's very easy. For G mod U, if you take HI of this, first, it's going to be, this is going to vanish for everything other than I equals to 0. And at I equals 0, this is all functions from G to C, where f of GU is equal to f of G for all G and G and U. Okay. So this should look really familiar. This is very close to what I wrote down for parabolic induction, right? So in fact, what happens is that G mod U has a left action by G, by just translating the cosets, and it has a right action by T, because T normalizes U. And so what it turns out is, and you should check this exercise, is that if you take the subspace of this space of functions, where T acts by some theta, this is exactly the same thing as induction from B to G of theta tilde, which was my R, B, G of theta. Okay. And so what we say here is that X and G mod U are Deligne-Lusztig varieties for SL2 FP. And tomorrow I'll tell you more about how to work with these. So yeah, thank you.
Are there any questions for Bruhat?
Yeah, just like this really stupid question, what is the notation for the induction? Is that P prime? If so, is that what is?
Oh no, sorry, you mean this sign?
Yeah,
Oh yeah, this is a tilde. Is that what you mean?
yeah, then what is this object, I guess?
Oh, this is a space of functions that I defined before. So this is all functions from G to C, where right translations by B results in multiplying the f of G by theta tilde of B. Yeah, so maybe it was previously written maybe up here.
Okay,
Yeah.
thanks.
Any other quick questions?